the sweetest thoughts of you and me. Memories of love above the city lights. Ooh, I try so hard to take it, but oh Lord, my heart would make.
Since 2008, Glasmanufaktur Brandenburg GmbH, as part of the Interfloat Group, has been producing high-quality glass for photovoltaic and solar systems, as well as for greenhouses at their Czernitz site in the south of Brandenburg, a historical glass-making region. 365 days a year, high-quality glass paints are produced from sand, dolomite, soda, cullets and other raw materials. More than 300 employees, as well as up to 60 temporary agency workers, work for GmbH, making it one of the region's most important employers. To produce high-quality, low-iron glass, it is necessary to use premium raw materials. Being a supplier for GmbH requires auditing according to ISO 9001. In the batch house, the raw materials are weighed and mixed following the company's own recipe. Batch feeders then carry the finished batch in the melting tank. In the melting tank, the batch is melted to a liquid mass at up to 1600 degrees Celsius. To this end, the GmbH melting tank is fired using natural gas and oxygen. This is currently the most environmentally friendly firing method for melting tanks and sets us apart from our competitors. Highly qualified employees monitor the production processes in the control room. The liquid glass is fed continuously to the two production lines where, at a temperature of around 1000 degrees Celsius, it is discharged onto the rolls with a width of 2.4 meters and a height of approximately 7 centimeters. Standard glass thicknesses are 2, 3.2, 4, 5 and 6 millimeters. Different glass patterns enable different applications. The pattern of the glass minimizes reflection, meaning the sunlight is guided into the glass and thus onto the PV or solar module. After rolling, the temperature of the glass is reduced to around 80 degrees Celsius by transporting it on water-cooled transport rolls and ceramic rolls so as to ensure break-free cutting. The edge cutters score the side edge strips and then break them off. The cross cutter splits the glass ribbon into stock plates. The first inspection takes place during this step of the process. The position and size of defects, such as bubbles or seeds, is registered and evaluated. Two fully automatic and computer-aided cutting lines make optimum use of the glass ribbon for each blank. This enables even small production series to be produced according to customer wishes. For finishing lines are able to flexibly accommodate the individual wishes of our customers. GmbH consistently seeks to further develop innovative products and improve the production process. A team of young, motivated engineers works closely with production engineers to analyze the current process. For our customers, the strength of the glass is very important. After all, the products must endure extreme weather conditions such as severe hailstorms. To achieve this, the glass is reheated to a temperature of over 600 degrees Celsius, and it's thermally toughened with huge amounts of cool air. Only top-quality products leave the works. Therefore, the automatic packaging line is subject to constant visual monitoring. In the packaging line, the glass is automatically rotated into the position required by the customer and then washed. After another automatic inspection, the separating layer made of paper or cord is applied only to the best glass parts. These are then packed automatically, either on L-racks or in so-called flat packs. A final visual inspection takes place manually. The finished packaging is covered with stretch film and is released for dispatch. Products for our customers are stored in an area of 13,000 square meters. In this way, the Interfloat Group ensures maximum flexibility and continuous supply capability. Our products are an important component of the photovoltaic and solar modules of all major European manufacturers. The glass that we produce protects plants and promotes their growth in greenhouses all over the world. The Interfloat Corporation's investment in GmbH Glasmanufaktur Brandenburg created an economic beacon in a structurally weak region. This was acknowledged in 2016 with the European Solar Prize. We are proud of our company and look forward to a bright future. GmbH, High Performance Solar Glass.
As the global climate challenge grows, the development of photovoltaic PV new energy is of great urgency. In 2006, Tongwei entered the PV new energy industry and has now become an integrated PV enterprise, engaging in the production of high-purity crystalline silicon in the upstream, high-efficiency solar cells and modules in the midstream, as well as the construction and operation of PV power stations downstream. With its leading advantages in scale, technology, cost, and quality, Tongwei Solar has formed a vertically integrated and complete PV industry chain. Tongwei Solar is accelerating towards an integrated layout and has now arranged the layout of module production bases in Hefei, Yancheng, Nantong, Jintong, and other places. After years of technical accumulation, scientific research, and innovation, Tongwei Solar now has two major series of module products: half-cell modules and shingled modules. Half-cell modules have advantages including low LCOE, high power and high gain, while shingled modules are featured by high power efficiency, safety and reliability, low lead and zero fluorine, and convenience of recycling. Tongwei Solar is also promoting TNC and THC technologies in parallel and actively exploring various cell and module technologies such as TBC, Perovskite lamination. Tongwei Solar has independently developed the TNC high-efficiency cells, the mass production conversion efficiency of which has reached over 25.4%. Among the leading manufacturers that have taken the lead in entering the HJT field, Tongwei Solar's HJT cells have achieved a maximum R&D efficiency of 26.07%. Tongwei Solar continues to update its technology pool with emerging ones and always stays at the forefront of the industry. Ranking on the Tier 1 list, it has currently obtained national and regional certifications in major markets such as Australia, Japan, and France. Tongwei Solar's high-efficiency modules are suited for household rooftops, industrial and commercial distributions, large ground power plants, etc., boasting a perfect and professional service system and a high standard of supply quality. Tongwei Solar can meet global customer needs in all respects. Tongwei Solar's high-efficiency modules have cooperated with multiple projects around the world. Its products are exported to more than 40 countries and regions such as France, Germany, the Netherlands, Chile, and so on. Carbon peaking and carbon neutrality goals have become a global consensus. PV brings together the momentum for green development to create a better future and achieve the sustainable development of humanity. Tongwei Solar. PV changes the world.
What is zero? It can be zero distance, bringing solar energy to every corner. It can be zero error, representing our attitude to the products. It can be zero destination, representing our pursuit of advanced HJT technology. It can be zero carbon, contributing to build a cleaner world. So what exactly is zero? Zero is the goal. A goal that drives us forward, fuels our passion, and defines our purpose to shape a net zero future.
Please take a seat, we are ready to start.
Se lo vuole chiedere, se no ci faccio un altro momento.
Magari proprio l'apertura sembra... So welcome today to the second day of the workshop. Yesterday was a very wonderful and full day, a lot of interesting presentation and discussion. I saw people discussing and very happy to continue the discussion during the breaks and the lunch. Today we have 3 sessions, and then in the afternoon the visit of Trisan. For who is coming to visit Trisan, there are 4 groups that have to go in this area to divide the group and go to the bus, but we will send you more information later. So I let Keining chairing this first session.
Okay, good morning, everyone. I hope you arrived here more or less dry. Today, the session, I'm very happy to be able to chair this session, which is looking into the future of the heterojunction technology together with Perovskite. Without spending too much time with myself, so I would like to maybe ask the first speaker, Thomas Allen from KAUST. KAUST is really very well known for its perovskite heterojunction activities, and he's going to talk, give us an overview. Yeah. So Thomas, stage is yours.
Okay, very good. Thanks, Keining. So hi everyone. It's a great pleasure of mine to be able to give you kind of an overview of the monolithic 2-terminal perovskite silicon tandem activity at KAUST. It's a work of a lot of people who I'll thank at the end. So just generally, monolithic tandems are typically processed in one of two ways. Either a PVD step is used to conformally coat either the entire perovskite or a part of the perovskite on like conventionally textured silicon. And that's kind of exemplified by the work from EPFL here and CSEM. Or the perovskite is solution processed on planar silicon. That gives the advantage of being very flexible in the perovskite chemistry, let's say, but you lose a little bit in current because of the suboptimal optics. And so we've developed a process where we do solution processing on textured silicon to try and get the best out of both worlds. And that's the kind of structure that I'll be talking about today. So you can see the kind of process here. We started in 2020 with a really great collaboration with the University of Toronto. And here you can see the cross-section of the device showing the top cell. Kind of the perovskite is such a significant concentration that it's quite thick and fills up the spaces between the pyramid texturing, which has been reduced down to about 1 micron in size. That gives us sufficient optical reflection, suppression of the front reflection, and also decent light trapping as well. And just in general, the perovskite structures that we've all kind of landed upon are in the PIN configuration, meaning that the silicon has the, at least we're working on silicon heterojunction cells, and where we have the P layer at the back, the N, which is typically nanocrystalline silicon in our case, at the top, and then the perovskite has the HTL, the perovskite, and then the ETL at the top. Okay, so these were the first kind of generation of cells, and you can just see, despite the fact that I said optically they're very good, you can tell that optically they were pretty bad at the start, but we were still able to achieve an efficiency around 26%. And I'll start by discussing a little bit the front side contact, the C60 contact. I start there just to emphasize that this is really the contact that is, let's say, the weakest link in every possible dimension, I would say, in the device. And so we started kind of trying to improve the front contact with the addition of a magnesium fluoride interlayer. This is the work of Jiyoung Liu, who went to work a couple of years ago with Longi and did some great work there. And so the magnesium fluoride layer essentially is used to displace the C60 away from the perovskite interface. And like for the silicon people, this is analogous to the defects that a metal will induce at the silicon interface, metal-induced gap states, let's say. Perovskites have a similar thing with C60. It's like a C60-induced gap state. So this is some DFT calculations showing the introduction of defect states within the band gap as the C60 is brought closer and closer to the perovskite surface. So with that, we were able to achieve a 29% cell, and obviously with some other optimizations. But C60 has other problems. Well, not only the gap states, but you can see here in the EQE, a lot of this loss in the blue response is related to very strong absorption within the C60. So C60 is not good in terms of recombination, it's not good in terms of optics, it's not good in terms of reproducibility. And so here is a work with from a postdoc in our group, Ahmed, where he looked at the reliability of the C60 process after repeated thermal cycling, so repeated evaporation processes using the same C60 source, showing a degradation, a steady degradation with increasing evaporations of the C60 source. And then a lot of chemical characterizations of the C60 showing that these fullerenes kind of agglomerate, forming different, like a C120, for example. And this introduces not only defects within the C60 itself, but also within the film. It limits the mobility, and you see a steady decrease in performance of the solar cells that I haven't shown here, but you can see in the paper. You can kind of get rid of this effect by using an ultra-pure C60, and so this is Barry Rand's contribution from Princeton to this paper. So using that very high purity C60, you can do repeated evaporations and repeated thermal cyclings without getting this detrimental effect, but you have to use the pure stuff. And also, depending, perhaps on many factors relating to the encapsulation, but you can very easily have delamination of the C60 interface because it's so chemically inert. There's very weak binding to the underlying and overlying layers of the perovskite, and you can see a lot of delamination depending on your process and depending on your lamination material. So C60 is causing a lot of problems. And in my opinion, they haven't in any way all been solved, and that's kind of where I think a lot of the remaining work will come from in the device. At least in terms of efficiency, let alone stability. Okay, so I'll just now move to the HTL contact. So with a lot of really great work done at HZB and with Kaunas, developing these phosphonic acid-based self-assembled monolayers, we have very nice HTL contacts now. And with some chemical modification to those SAMs that are deposited and anchored to the TCO of the underlying silicon cell, you're able to get very nice tunability in the valence band position. And so this is great, not only for passivating defects, but again, also aligning the energy levels at the contact interfaces. And this is good not only for efficiency, but also stability, which I'll show here. So this is work of a PhD student, Lewis, recently published in Joule. And so what he did, he took the two kind of more extreme valence band minima SAMs, so bromine 2-packs and MeO 2-packs, and with a mixture you can tune the valence band position just with a mixture of the two SAMs in the solution. With this, you can choose your respective SAM ratios to tune the valence band to match the valence band of different perovskites. Because usually when you're changing the band gap of the perovskite, the energy level that changes most is a deepening of the valence band. And so what Lewis showed is that when you tune the energy levels to match the energy levels of the perovskite for the contact of the valence band, in all of these situations, you get a higher efficiency, but you also avoid halide segregation, or at least suppress the rate of halide segregation in the perovskite bulk. Okay, so now I'll just shift gears a little bit. So now this is just on silicon now. So this is SAMs, the same 2-pack SAM as an ETL on silicon heterojunction cells. So here, Adi, my PhD student, did some great work where the idea here is that the SAM now is anchored not to the ITO and is pointing towards the absorber. It's anchored to the absorber, which is now silicon, and it's pointing towards the contact, and that changes the direction of the dipole. So instead of collecting holes, we're now collecting electrons in the silicon. And so this SAM is anchored on amorphous silicon that's been oxidized just very easily in our box oven that we do that we use for the annealing of our metallization. Okay, and Adi was able to demonstrate with this a very low, for us, contact resistivity, around 65 milliohm centimeters square, which is significantly better than our nanocrystalline silicon, which is unfortunately significantly worse than state-of-the-art nanocrystalline silicon, but so be it. And so with that, he was able to translate that into higher fill factors in control devices. The optics are not very good, so there's a decrease in the infrared response of the cell. But in general, this is a very simple process. You can do it dip-coated, blade-coated, spin-coated, however you want. It's very simple. You dip the SAM solution in, you wash it off, you anneal it, and you're done. Okay, so now we're going back to tandems and back to perovskites. So we found an optimum for anchoring the SAMs onto IZO. We think that's largely due to the amorphous nature of the IZO and the fact that you then get better coverage of the SAM on the IZO layer. And so with that kind of optimization, we were able to improve the fill factors in the tandems. And then, as I said, our initial batch of tandems you could see were optically pretty poor. Now you can see a much better improvement just visually. And that's coming from an optimization, of course, at the top, where we thinned down the TCO, increased the thickness of the magnesium fluoride, and very much tried to decrease the thickness as much as possible of the C60 ETL. And then at the back, we implemented a rear reflector design with the magnesium fluoride displacer, which I'm sure a lot of you are familiar with. And so both of these optimizations together conferred about a 1 milliamp advantage to both subcells. And so now we're kind of getting towards or even slightly above 21 milliamps for the tandem, which is more or less current matched. Okay, and then finally, ESMA did some great work very recently introducing an additive into the Perovskite solution. So this is methylene diammonium dichloride. This is a additive very much advocated and very well applied by Sangil Sox group to very good effect. The initial thinking was that the MDA entered into the A side of the perovskite, but some recent work here from Henry Snaith's group shows that actually this MDACL undergoes some, at least for me, complex chemistry. I'm not a chemist, so I can't really tell you, but in the solution it forms this molecule THTZ. They showed that on 4-mamidinium single crystals, and that conferred very much a stability advantage onto the FAPI single crystals. We showed in our triple cation mixed halide perovskite that this is also being formed. And we believe that this THTZ molecule, because of its basically its shape, so its cyclic nature, means that it's able to more strongly bond to the halides in the perovskite, and it's able to bond to more of them. And even with a very slight concentration that we're adding in our film, it confers photostability, thermal stability, and photothermal stability to the perovskite, and increases the radiative efficiency of the perovskite, as I'll show, from about 0.4% to 1.4%. So that's a huge increase in voltage. And with that, we were able to make the 33.7% cell. So the difference between what I'll show soon, between the 32.5% cell and the 33.7% cell, is the MDACL additive in the bulk. Okay, so where is the efficiency heading? So the radiative limit here is calculated. You have a kind of broad optimum around 42.5%. That's not including radiative coupling, which tends to give an even broader optimum and a slightly lower efficiency. If you limit yourself to a state-of-the-art silicon heterojunction bottom cell, our bottom cell is not state-of-the-art, unfortunately. But if you were to do that, you have only a very small efficiency penalty, and even if you limit yourself to reasonable band gaps, you're still able to achieve, or the radiative limit, let's say, is of the top cell. The tandem cell is still over 39%. So we did some modeling, just simple diode modeling of our tandem cell. This is the pseudo JVs from EL, from which we extracted the diode parameters. Again, you can see here, this is the difference between the 32.5% and the 33.7% cells, where we can see that significant increase in the radiative efficiency of the top cell. Another interesting thing I think about this additive, this is comparing the JV curves very much zoomed in around maximum power point. So we would always see this kind of slope in the JV that kind of looks a little bit like a shunt, but it's not a shunt. It doesn't show up in the dark. So it's like a failure of superposition between the light and the dark JVs. That almost completely is suppressed in the 37.5% cell, and with some drift diffusion simulations, I think it's probably likely a result of a suppression of the mobile ions in the perovskite to something that's now almost negligible, at least having its impact on the JV. So if we were to swap out our bottom cell with a state-of-the-art heterojunction cell, we can kind of imagine an efficiency. So this would be a line of sight improvement that will happen very soon, I'm sure, of 35.5%, let's say, roughly. And then if we just have another thought experiment where we increase the radiative efficiency of the top cell further from, okay, so this was the 32.5%, about 0.4%. With the additive, it increased to around 1.4%, like a very large increase. But we're still a long way from more narrow bandgap perovskites, so 1.55 eV perovskites. In our lab, this is actually an old result, but that's around 6% radiative efficiency. It's now even higher. But if we were to achieve with the wider bandgap perovskite a 6% radiative efficiency, we can expect something close to 37.5%, we think. That's with the state-of-the-art bottom cell, of course. Just quickly, I'm running out of time, but I'd just like to point out some very recent work published in Joule, which is on blade-coated perovskite silicon tandems from Anand. And this is the first, I believe, the first certified efficiency for a blade-coated perovskite silicon tandem at 31.2%. If you're interested, please check out the paper in Joule. And with that, I'll finish, and I'd very much like to thank everyone, past and present, who has worked at KAUST, and that this has been a real team effort. And thank you very much.
Okay, so thank you very much, Thomas. We are running behind schedule, but I think we can accept one question if someone wants to ask anything. Yeah, please.
At a certain point you put lithium fluoride instead of magnesium fluoride. I mean, is the same?
More or less. We just find it is more repeatable and somehow induces less hysteresis, but it's doing the same thing. Why? What's the difference? I have no idea. Just an optimization. Yeah.
Actually, the same question I had too. Okay. Would you be able to get 34% with magnesium fluoride, in your opinion? Because all the highest recorded efficiencies are now with lithium fluoride, you know?
Honestly, I don't know. Like in our lab, probably not. Maybe not. But it depends. I think it's just a little tricky thing with the evaporator. Like maybe if you had a separate evaporator purely for magnesium fluoride, it would be okay. But obviously, no one does that. So It seems like the lithium fluoride is a bit more robust in that regard.
Okay. Thank you very much. So let's thank Thomas again.
Thank you.
Okay, so next we have Professor Aldo Di Carlo from University of Rome. And he's going to talk about mechanically stacked two-terminal architectures for perovskite silicon tandem. So very interesting. So,
thanks
Professor?
really a lot. It's not simple to speak after KAUST, but I will tell you what we are doing and the talk. Okay. So I will speak about the activity we are doing on 4-terminal and 2-terminal perovskite silicon heterojunction. The activity has been done mainly by Erika Magliano, as you will see, and then you can speak with her. She is here in the conference. Okay, so one of the problems we have to face doing the tandem is the following. So usually from perovskite community, we are used to have a back metallization. So we need to remove back metallization to make semi-transparent solar cell. And then we need to find a way how we can gently deposit a transparent electron on the perovskite solar cell. So we have seen that this is also the problem faced yesterday in the silicon community. So it looks like that there's a common problem between the two communities. So there are several ways to do it, but the problem, where is the problem? So you can see here, when we use the conventional sputtering, RF or DC sputtering, so we have this kind of plot efficiency as a function of power density, and then you see if this is the reference cell with the evaporated metal contact, when you sputter ITO on the top, so for low power density we need a lot of cycles, so we have a UV plasma effect. When we go for a high power density, so we need less cycles to get the same thickness, but then we have a lot of ion bombardment effect. So at the very end there is a maximum, but still we are quite below the efficiency of the one evaporated. So then to solve this problem, one can use, as I said, low power. So for example, in this case, if this is the IV characteristic for the opaque cell, so we can get with 0.4 watt per centimeter square an IV characteristic which has no S shape as we get for large power. So this is low power still with sputtering, but one can use different technique. For example, pulsar laser deposition. Pulsar laser deposition is quite gentle, and then you can see with sputtering you have S shape. With PLD you resemble very much the characteristic of the opaque cell. Or one can use ion beam sputtering. So this is also what we tested, and this is RF sputtering, and this is ion beam. You can see that ion beam also is a very gentle way to deposit the ITO on the top of the solar cell, the perovskite solar cell. But I mean, the usual technique people use, and we have seen also before, is ALD, atomic layer deposition. The point is ALD, it's quite could be quite expensive equipment. It's quite complex also to run it. So the idea is, can we replace ALD with more simple solution that everywhere in the world can do tandem and contribute to the development of tandem? So the idea is to have a buffer layer, and the buffer layer could deposit in two simple ways. One is a thermal evaporation of the buffer layer, so you protect the layer from the sputtering via the buffer layer, or you can use solution process nanoparticle. I will show you these two solutions. The first one is to use molybdenum oxide, which is quite conventional, but also vanadium pentaoxide as a buffer layer. So we use these two material, and then you can see without buffer layer, and we have spattering here, so you have S shape, which is damage of the layers. But when you use molybdenum oxide or vanadium oxide or pentoxides, so you see that you resemble the conventional IV characteristic. And the efficiency, you see the efficiency also when you use these two materials is quite aligned with the opaque thermally evaporated electrode. So you see you can get the same, almost the same efficiency with both vanadium and magnesium, molybdenum oxide. However, there is a big difference between the two. So this is the light soaking at 50 degrees. And then you can see that without buffer, you have this kind of behavior. And with molybdenum oxide, you have a very strong reduction of efficiency. There is a reaction, which is quite known. But with vanadium oxide, I mean, you have much better result. So vanadium oxide is one of the choice for us to use as a buffer layer. Another way to do it is to use a nanoparticle instead of ALD. And we were testing as a buffer layer different nanoparticles like tin oxide, azo, and zinc oxide nanoparticle. And then you can see here, so this is the efficiency of opaque copper on BCP solar cell. And then you can see zinc oxide doesn't work as a buffer layer. Tin oxide works, but not so well, but azo works quite well. You see this commercial azo nanoparticle N21X from Avantama works very, very well. It resembles very much the same efficiency as the opaque solar cell. So in this way, together with Enea, that was providing the bottom cell is polish on one side, on the other side is not polished. So we were doing the full tandem by using azo nanoparticle instead of ALD tin oxide, and the efficiency we got was 25% at MPPT, which is one of the best for the polished silicon tandem with perovskite. Okay, so this is a way to do it. There is before going to the next tandem solution, I want to show you something that could be the next step for to put perovskite on silicon. So we were spending 4 years to set up a molecular beam epitaxy of perovskite, and this is one of the first example of perovskite. Is a large band gap perovskite on the top of silicon, and this is an epitaxial grow of perovskite on silicon. There is a buffer layer of silicon dioxide. Without this buffer layer, it doesn't work epitaxial. And then I want to show you the diffractogram, the XRD plot. You can see the XRD plot of this perovskite is very narrow. So the width, so if we zoom it, the width of this line after the convolution is 0.035 degree. So it's really a crystal structure, but it's an epitaxial layer grow on the silicon 111. So is it possible to create epitaxial perovskite? And then I believe this will help a lot, both from physical point of view, but also to have very better device. And this is a model. Okay, so there is another way, as I was saying before, to do in a simple way to do the tandem, is the following. So we realize the perovskite solar cell independently and from silicon solar cell, and then we do wafer bonding between the top perovskite solar cell and the bottom silicon solar cell. So this is this is the top perovskite solar cell, and then we cut part of this wafer, conventional wafer, so of silicon solar cell. So one can do good efficiency also in this way. Let me show. So we started some years ago with a 24%. Then we improve adding the buffer layer to get a better ITO. Then we add 2D material. So 2D material to change the interface property to adapt better the work function of the layer, and we use graphene and also mixins inside. And then we move from mesoporous to planar architecture, and this is the last results we are trying to communicate. So we can get 31% also by using this very simple, you can do every time in your laboratory, very simple way to do the tandem architecture. Let me conclude for the 4-terminal configuration. So for the 4-terminal configuration, and actually it's possible to go from a typical configuration of the 4-terminal, but to match the voltage of the top cell with the voltage of the bottom cell, and to have a 2-terminal configuration at the junction box. So this is something that, for example, Toyota is exploring very much. And in fact, we found that this is a very interesting way to have a 2-terminal with a configuration which resembles very much the 4-terminal structure. So we have done some examples, some experiment in this way. Let me show. So we were creating semi-transparent modules. So it's something like 10 by 10. And this is the semi-transparent IV characteristic of this module. Then we combine 4 of these modules to cover one silicon solar cell. And this is the final configuration. You see, in this case is up to this case is 4-terminal configuration. And then you see the final efficiency on this large area was 20.88. So the mini panel was 13.1%. It was not the record that we got before, but the filtered silicon solar cell was 7.78. Then this is just a building block. Then we take this building block and we put for this building block to create a larger area 4-terminal panel. And this is the 4-terminal panel we were developing in this way. So we create 4 of this terminal and 4 as a perfect voltage matching. So in this case, you can connect these 4 and to get a 2-terminal panel. So let me show you the results in this case. So So we started with a silicon heterojunction panel efficiency that was 18.90%, and then we had the perovskite on the top. Without albedo was 19.5, but of course the silicon solar cell was bifacial, was the enel or trisun cell, and then with albedo, so you can increase, of course, the efficiency. Of course, the efficiency, this is fictitious efficiency because it's referred to one sun, so 1,000 watt per square meter. Now we shipped all this module in Crete, and then we are testing this outdoor to see the problem from lamination, contact, and all this extrinsic property of the tandem. One can get a better results. I mean, one of the problem is geometrical fill factor. So let me rethink a bit to the geometrical fill factor. So the point is you have this dead area when you do the module, okay, and electron moves from one cell to another in this way. So, but this is not the only way you can think about a module. Imagine you can do this kind of geometry. So electrons that stay here moves to this point, which is the only point that is connected to the next solar cell. So in this way, you have a discontinuous P2 pattern, and with this discontinuous, this is a collaboration with Solertics, so with a discontinuous P2 pattern, you can get a 99.6% geometrical fill factor. So this has been transferred to Solertic, which is a company part of Futurasan. And then you can see, so it's possible to create a semi-transparent for 4-terminal configuration, which is at the minimum panel level with 90.9% of efficiency, scaling a little bit less, but I mean adding RC, you can get 80%. And with this, on the 5x5, you can get 30% efficiency on the tandem configuration. So 5x5, it's possible, even in 4-terminal configuration, to get 30% efficiency. So I can conclude now. I mean, I show you that it's possible to use simple way to create tandem. I show the mechanical staked, but also the use of azo nanoparticle to avoid the use of ALD. And also with mechanical staked, you can get more than 30% in a simple laboratory scale system. Thanks a lot.
Okay, thank you, Aldo. I think these are innovations that we should foster more. Yeah? So we can have 1 or 2 questions. Anyone? Yes, please, Thomas.
So for the mechanically stacked 2-terminal, have you tried getting rid of the metallization on the silicon and having a conductive adhesive between the 2 cells? And
thanks a lot. We were trying a lot.
Right.
So so far, I mean, the best is still with the grid. But this is, I completely agree. This should be the next step. I mean, but we need to find the right material.
Yeah, what are the challenges that you've faced there? What challenges have you had in taking that approach?
It's a very practical one. I mean, with the grid, I mean, you do the mechanical stick, and then you can change a lot of cells. I mean, and to find the right one. When you stick one on the other, is that one. I mean, it's so then. I mean, it's you need to do a lot of tandem to find the right configuration. So and also the optical losses we have. I mean, so we need to have a conductive layer. Should be very transparent, and so far we were working with bidimensional companies, so very a lot. I mean, to find it, but so far we didn't find the right way to do it. But I mean, I completely agree with you.
Okay, so I actually also had a couple of questions, but I think for later. Yeah?
Okay.
Okay. Thank you, Aldo. Let's. Okay. Next, we have Dr. Yuelong Huang. Yeah, he's the founder of Phoenix Solar. I would say a rising star in equipment manufacturing for perovskite Heterojunction-Tandem. So, Dr. Juan.
Okay. Thank you for the invitation. So, we are a very young company. So today I want to show something what we have done in our small team. Yeah. So the company is just founded in 2022, 2 years ago in summer. I with two of my PhD students and two postgraduate students together, we started to start the business. So actually, I have been in heterojunction business since 2001. So in Hagen at that time. So we are the earliest team in Germany making heterojunction at that time. Later on, I joined Jülich, Forschungszentrum Jülich, the same group like Kainin. Yeah. Then in 2008, I went back to China to start the manufacture of micromorph tandem solar modules. 100 megawatt at that time is first 100 megawatt level factory in China, maybe also in the world. Yeah. Then in 2016, then I go back to academy in the Petroleum University in Chengdu. We start the Perovskite research. When we are doing this research, I found it very strange because every student doing the same recipe but have different results. Yeah. And even the result change from summer to winter. So I think there's something wrong. We have to change. So finally, I think we need a good equipment. We need good, reliable material. This is what I'm doing at this moment. Yeah. So maybe about the history about the tandem cell, I don't need to highlight anymore because two professors already given a lot of information about 2T, 3T, anything. So I just jump to what we are doing. So actually, if you look at the publications, the highest efficiency solar cell, tandem cell, they are usually made by one step. Then, but if you want to make mass production, it's very difficult to make a one-step process. So then more and more company, a team are using the two-step process, or namely first step with thermal evaporation, then slow down. Of course, there's also many teams are trying two-step. They only use the dry process. They don't use slow dye. Yeah. So this is the general procedure for two-step. If you combine the evaporation and the slow dye. So the problem is everybody is asking, when can we have the mass production? But in fact, when we have this tandem cell from small cell to big cell, not only for tandem cell, but also for single junction perovskite solar cell, you have big problem when you want to scale up. From small module to big module, it's always a lot of technical issue, engineering issue, and scientific issue. So we see a lot of problem, and we try to help solve the problem. So from 1 centimeter cell, a square centimeter cell to the 4 sides. So this is what we reached with our partner 4-side module cell. So here's I just showed something about the slow dye. The photo was taken by hand by cell phone. Therefore, you see a lot of shaking, but in fact, the machine itself is stable. This is a slow dye made by us. So when you are making the 4-side slow dye, then if you look at the SEM, X-ray, XRD, you can make good film. But the problem is that you cannot make a very good film for the 4 wafer. It's always difficult to avoid the contamination from rear side, or to make a full coating, especially in the age. So therefore, all the company like Tongwei and Ms. Watson, they are looking for good equipment. They will ask, how can you minimize the age of the coating? Means the age which is dead, almost dead, yeah, is with bad quality. Because if you make a single junction module on glass, you will remove the side, the edge side, for 1 centimeter or half centimeter. But for silicon, it's not possible. You have to make very good film for the whole wafer. So this is a problem. But therefore, we think maybe for mass production, to use slow die is not the best solution. Not only because the edge side, also if you use slow die, you always need to make positioning the head on the wafer, and sometimes the wafer maybe is not so flat. So you have to handle everything technically. It's quite difficult. Of course, we will have some solution to make a better slow die, but we also show you some other technology we can make a similar or a good quality, but a very good control of the film quality. Of course, to make the multi-source co-evaporation of PVK layer to achieve a band gap tuning, yeah, this is also, everybody is doing that, but to make good evaporation for large area, then you again have problem. To make small area, to make a record cell is not, everybody can have many, you can use lots of technical to do that, but to make large area, then it's difficult. So actually we have helped our partner to make the size for about 1 square meter size. So you put lots of wafer on the chamber and make a 1.3% of homogeneity to deposit all these kinds of inorganic salts or C60. Or yeah, so this is quite a lot of work. Yeah. Okay, this is another thing I want to show you. We also develop in-house inkjet printing coating. So to use this, it's very fast, because exactly it's very fast. You can make something like 1 minute. You can make so according to our calculation, 50 meter print. So you can really make a very good film. And of course, there's also some other companies say we can make a film, but what's different, I will show you later on. So our company, as a startup company, we are not doing the film. We're always making the good cell. So this is we are reaching a similar efficiency compared to slow die. So we do not only show you we can print good cell. This is what we are doing. So okay, so actually we have a lot of research internally ongoing at our Phoenix Solar. We have about 60 scientists working in our small company. Yeah, we are, working for the process, not for the equipment. So we have about 80 engineers developing equipment, but we have 60 scientists developing process materials. Yeah. So this is what we have built in the past 2 years in-house with our knowledge. We all the core process equipment are done and ready to show you. So what we have now is we have 3 lines actually open to the Chinese, and of course, because I didn't do any advertisement before the nature conference last month, so we only send a message to some professor, say, we have this single junction or tandem cell line, you can come to try. Yeah, but now about 20 teams from China, the companies or university teams come to our lab, and we hope then for single junction, make 30 by 30 centimeter mini module. Most of them has reached 20% efficiency, module efficiency. Most of them. Also, we have also helped a lot of colleagues make tandem cells. Yeah. So actually, to make a good film, it's not that easy. To make for the publications, you always make in spin coating. But when you are making slot die, larger area, this is only 30 by 30. When you are making even 2 square meters slot die, then you really need to understand what is happening in environments, what's happening if you use a different additive, use a different solvent, the result is completely different. So the good thing is our team has tested almost all the papers published in Nature and Science who publish good results with small cell, record cell. We tried to make a bigger module. We try everyone. We know which recipe can be scale up, which cannot be. So we did a lot of effort to do that. Yeah, and therefore we understand different solvent system or chemical. You need to use different parameter, and we use a supercomputer to calculate the parameter for slot die to finally find out the real process parameter. It's very expensive, but we did it. Of course, professor said tin oxide should be replaced, but in fact, we can make a reasonable price with ALD. It's affordable to ALD to deposit. You can make very good film, homogeneity, but what's important is that, very important, use tin oxide deposit by ALD. You immediately have very good encapsulation. It's very stable. Even without lamination, we keep it in air for half a year. Nothing happen. So to deposit very good tin oxide with ALD, we think it's very important. Yeah. So of course, there's a lot of tricky thing, especially when you are using different type of ALD, temporal or spatial. But we have both. We have developed both equipment. We are able to deliver up to the wide is 1.2 meter wide ALD. Yeah, for both kind. Okay, sputtering is a boring thing. Everybody say sputtering is very easy because many company, many team has used this sputtering for 20 or 30 years. Yeah. But in fact, it's not that easy. To make nickel oxide, to make good nickel oxide, in fact, it's not easy, especially for large area. We have some clients, they bought equipment for a mini module, a pilot line, and deposit nickel oxide, and then they only can make 10% efficiency. Then when they come to us, I just go there, look at the data, then I say, I send you the glass deposit with our nickel oxide. I guarantee you 15% efficiency. Immediately, they reached 15% efficiency with their everything the same. But I'm sure if they use our ALD to deposit tin oxide and slot die, I can guarantee them 19% efficiency. I mean, a 30 by 30 centimeter module. But I see their solvent system is not that good. I cannot guarantee 20%. But with our baseline, we are something like 20.5 or something. Okay. So this is our team, so part of our team. So we made lots of modules for lots of clients. We do lots of research for laser, for deposition technology, for material. We even develop different material with some teams. I give about 8 university team, give them not big money, but million RMB something to develop some process for us. So although I'm a small startup company, yeah. So of course we publish something. So what we are doing is always make the perovskite solar cell in air without real very strict environment control. If you don't do that, then it's meaningless. You have to make everything in air to use a lower cost. So this is the teams who already use our equipment, make good efficiency with large area, and also some of them make good tandem cells. Like Peking University Professor Zhou always thanks our company in her paper, something like. So, and many professors now in China is building up startup companies. They are buying our turnkey line for single junction, perovskite solar cell, yeah, and tandem cells, yeah. So this is some another showcase, yeah. So this is one of our clients work with our equipment, use our standard baseline. We show them this result. We make it together. Okay, this is another story. We can make a good module every day. The good thing is that we don't have really any fluctuation. Always keeping quite a stable efficiency, yeah. And in fact, all this result is without anti-refraction, even some of them without the passivation layer to make good results. Yeah. So also we help our clients, so use our baseline technology, use flexible perovskite mini modules. Yeah. So this is our company. We want to be the experts in the perovskite solar cell mass production solution. So actually, we provide, in order to guarantee the equipment reliability, we guarantee the baseline so that to help our clients to avoid lots of unexpected influence. Yeah. Yeah. Thank you.
Okay, thank you very much. Due to time issue, maybe one question that can be answered short. Anyone? Okay, maybe just one thing I wanted to ask. Do you think in the future, in the mass production of perovskite silicon tandem, the laser edge remove would be necessary, or you think rather not?
Yeah, this is another thing I didn't show in this picture. Yes, we really after slow die we want to use laser edge cleaning to. On one hand, we can clean the perovskite. On the other hand, we can do some passivation. Yeah, this is what I'm in our lab doing. So we have lots of new things. I only show something we have internally tested, certified, then we show. So this is the direction we are doing.
But do you think that would be mandatory?
I don't know.
Okay.
I don't know. So because for tandem cell, I don't think we will have mass production in 2 or 3 years. But for single junction, maybe yes.
Okay, so let's thank Dr. Huang again. Huh? So Next, we have Chris Case from Oxford PV. So Chris is an old friend of this workshop, and he has some schedule issues because he's traveling all around the world. And hi, Chris, can you hear us?
Unmute, yes I can. Can you see me also?
Yes, we can see you, and we also hear you. So, Chris. So anytime you are ready, can share the screen and start. So Chris Case.
Just have to share the correct screen. I don't know why I don't see. Share. Okay. Is that sharing? Nope. Try again. Sorry. Back to the Zoom screen. Did that work?
Yes, it's not
Okay.
in the presenter mode
Right.
yet.
Okay, so let's do that. Is that working now?
You're sharing the maybe yes.
But is it showing the presenter mode? Is that the problem?
No, not yet. But maybe you need to you need to duplicate the show
Yeah,
slideshow, and then it will work. Yeah.
That work?
Yes. Yeah.
Okay. All right. Of course, I can't see myself, so I apologize for that. So again, thank you, Kaining, and apologies for not being there in person. And thanks to Cosimo and the rest of the organizers and the sponsors. One thing for sure is guess that you'll have a very good hosting and food where you are. So apologies. I won't blame the recent horrible results from the US elections for my not being there, but anyway, whatever the reasons. So we heard some technical talks from Aldo and Thomas on the perovskite, heard a rather different kind of talk on equipment to support the tandem solar cells. And of course, I'm going to talk about the commercial side and production side of tandem solar cells and maybe keep everybody excited about the future of this technology. So I always like to make sure I begin with just a reminder of why we do these things, and that's of course decarbonization and our hope to address the climate crisis. So let me talk just quickly about the company and Oxford PV and how we got to where we are. We're a 2010 spin-out from the University of Oxford, co-founded by Professor Henry Snaith. And you see two buildings in the bottom there. On the left is our UK R&D and headquarters, and on the right is our factory and pilot line and demonstration and development facility in Germany, just outside of Berlin. Of course, subsequent to Tom Miyasaka's discovery of the role of perovskite in solar cells, lots of people by 2014 became quite interested in the perovskite material. Oxford PV was not working initially in perovskite, nor was it working even on tandem solar cells, but it was a dye-sensitized BIPV product. But with this sort of recognition of the role of perovskite, and of course, the further recognition that everybody should understand the ultimate and impending silicon theoretical efficiency limit for standard single junction solar cells, the idea became clear that we could try to boost the efficiency by moving to really the only viable way multi-junction solar cells. And that's, of course, the path we've taken. So we've been working multi-junction perovskite on silicon cells since 2014, so roughly 10 years. But it's important when I identify that the future is high efficiency, just to remind everyone that efficiency is actually important, despite the 1,000-fold reduction in the cost of PV based on silicon in the last 40 plus years. The cost of the solar cell is a small part of the cost of a system, so reducing the cost of the solar cell further doesn't actually impact or reduce the cost of the energy that's produced, but raising the efficiency does. And just remember, you have only limited space on your rooftops, and the reality is fields where the utility installations have been placed also have limited available space when they're close to grid connections in the suburban areas. Back in 1883, this guy, Charles Fritz, installed a solar array made of selenium panels on the rooftop of New York City. So he had a dream to convert the world and decarbonize from fossil-based fuels. And that's more than 100 years ago, obviously. So it takes a long time to get these technologies commercialized. And look at this. Heterojunctions, right, for this conference date back to 1975, IBC 1985, PERC 1988. Yet it's only been 10 years on perovskite, and part of that, I think, is we've pushed very hard to develop a lot of things in parallel. So before we even achieved, commercial results on small devices, we were building a scale device. Before we had our scale devices, we built the pilot line, and before the pilot line was fully operational, we started to build a small production line, and now we're planning an actual much larger factory. So we're trying to move very rapidly. On the left-hand picture, by the way, is our first tandem solar cell that convinced us we could do this with less than a year's worth of work back in 2015. And then, of course, we continue to show that these actually were boosting the performance by more than 20 or 30%. And the first thing we did, by the way, and this is again to move fast, was to scale the device. So we moved to a 100 square centimeter area within the first year, actually. That convinced ourselves that there was no fundamental problem to scaling, and you've heard some comments on the equipment side. There shouldn't be a fundamental problem to scale, so that's what we did. But the other, and I think, critical decision that we made, again very early on, was to select what is, of course, the best solar cell, the heterojunction, predominantly because of the highest efficiency solar cell and the presence of the natural tunnel junction in the form of the TCO or ITO that's in place on the heterojunction. We remain convinced it is the best solar cell, although you can definitely integrate this on other types of silicon solar cells, as we've done. Built on the first heterojunction in 2016. Of course, three components to PV, right? Efficiency, cost or price, and reliability. Well, the efficiency and the cost come almost for free with perovskite, but how do you demonstrate 25-year performance without 25 years worth of field performance? But the good news is we had very early indications that these materials could be quite stable. This is from 2016, and what you see is some of the devices actually perform very well from a degradation standpoint, but not all. So the fact is we had a lot of variability, and variability meant we had to figure out what was the contribution to the variability from defects and failure mechanisms. So we broke the device down into different components, starting all the way from the perovskite crystal structure through the absorber, the device stack, of course the cell and the module, all had identifying the key defects in each of those areas, the key ones, not all of them, the key ones, and then putting them together to address them. Of course, this is a complicated problem because now you have the addition of light and temperature and temperature changes to the model. So of course the best way to address that is to use machine learning to sort of accelerate that. When you combine that with accelerated stress tests, we're able to rapidly improve and reduce the losses we have in our devices. More than 80% of the work we do is based on improving the reliability of the product, not improving the efficiency of the product. And this is the tandem solar cell. This effectively is our product. This is a certified full size, full area, single device, two terminal, direct perovskite on silicon tandem solar cell with nearly 29% efficiency. This is, of course, what I'll describe going into our commercial product. going forward. You have to make modules too. We decided we didn't want to invent any module making, so we adapted conventional module approaches. The only difference, or not differences, but we selected early on double glass, clear that was going to be the most reliable form of encapsulating these products, and we rapidly moved from encapsulating just a few cells to making mini modules and ultimately full-size modules using conventional assembly techniques and materials and just conventional equipment, stringers, testers, they have to be unique for this material, and of course, laminators and full-size module makers. Now, we've been focused on the tandem solar cell and the modules made from tandem solar cells. A lot of other companies focused on large area, a monolithic product, although they're also working on multi-junction, in many cases, 4-terminal devices, performing very, very well and very commendable performance and commendable reliability from these other companies. But again, our focus is on the 2-terminal silicon-based products. So let me talk a little bit about the production. We have our own heterojunction production line in the factory in Germany. It's a relatively small line, but it's used to produce our bottom cells. We don't necessarily need to produce our own bottom cells, but when we started, it was very difficult to acquire them, so we've chosen to do it that way. We've put in, more than 500,000 hours into this development, hundreds and hundreds of thousands of wafers to produce what we've done, and countless experiments going into that. Now, this is actually something I don't usually show, but I'm sharing you some production data off the production line from about 18 months ago. And of course, you can see the distribution looks reasonably normal, but there's a portion of the distribution at the bottom where the devices are just, breaking, et cetera. So the yield is not as high as we want. So it was around 80% at that time. And of course, the distribution peak is still not as efficient as we'd like it to be, but that was more than 18 months ago. And I can tell you that we've addressed all those problems and moved the efficiency up to our target efficiency. And this is a module. It's a 25% full area record module based on these. So this is a 60 cell module based on the same tandem solar cell that I just showed you. And in fact, we've gone beyond that. This is a 27% full-size module made with these same solar cells. The only difference here, these are production cells, but they've been sort of hand selected or cherry picked off the distribution, as you might imagine. So these are at the very top of our distribution capability, but they represent what modules will be like in a year or two when the production capability improves. We've gone through all the 61215 and 61730 sequences for reliability, both on small devices and on full-size modules. Unfortunately, you cannot fully certify at the moment a tandem cell on a large module area because the certification is only in draft form, but we'll complete that as soon as we're able to get that specification completed. Here is, though, just to give you an illustration of what happens and that the modules are performing well. This is after thermal cycling. This is the full thermal cycling test from a certification run, showing you the before and after images from these devices, full-size modules, and nothing apparent or bothersome. We've been testing modules and cells outdoors for more than 5 years. I think this is only about a year or two's worth of data, and we don't see in the most recent builds any evidence of or degradation that would give us any concern or customers any concern about meeting their expectations for performance and reliability. This is the spec sheet. So the module is a utility size module that we're currently producing, 545 watt, 72 cell full size module. And if we showed it for the first time in Munich at Intersolar this year in June, and what I can tell you is we've now sold, important word, sold, shipped, and delivered hundreds of modules to our sort of first launch customer. They're a very large utility customer in the United States, and they will be going into a 20 megawatt grid connected installation in the United States sometime later this year, but the modules have been delivered. Most importantly, and I just emphasize that word, once again, sold these modules, so that's good. What comes next? Well, you've got to build bigger factories, of course, And the reason is, and this is what the Chinese, of course, have done so well, and what they've learned is to get the most efficient products, you have to have large-scale manufacturing. And same thing that happens here. To reduce the levelized cost of energy, which is the parameter we should all be discussing when we talk about the modules and not their costs, but actually the price of the energy that's produced, you have to scale to larger factories. It's certainly at the gigawatt level. So we've done our plans. We've got factory designs up to 5 and 10 gigawatts for perovskites, using different kinds of tool sets. In fact, the footprint for the factory, this is a gigawatt footprint, just over a gigawatt, actually would fit in our existing factory footprint, but our plan is to, of course, build somewhere new. We have not selected a site or announced a site. We're considering sites predominantly in Europe and the United States at the moment, and just making choices based on attractive things. This is our roadmap for efficiency for both small-scale devices and the commercial devices. You can sort of just remind yourself 30% in 2030. That's the target for at the gigawatt scale for these things. We were very lucky to have a very strong intellectual property portfolio developed early at the University of Oxford. We have more than 600 patents. And what the target for decarbonization for net zero is something like between 35 and 70 terawatts. And to do that, we would need to install between 2 and 3 terawatts per year for the next 15 years. There's a lot of business out there. We can't do all of that, and we're very much open to collaboration and joint ventures and licensing our technology going forward. I would say, back in 2010, there really wasn't anybody or very many people working in this perovskite field. A jump ahead, 10 or 14 years, there's hundreds of companies, and this doesn't represent really all of those companies that are out there. But certainly we believe this is the best thing. And the more we develop these high efficiency solar devices, the more we can accelerate the adoption of solar and hopefully meet those net zero targets by 2040. And I just close with my closing line, the future is all electric. Okay, that's it. I came in 14 minutes, 53 seconds.
Okay, thank you, Chris.
And did the sharing stop?
Yes. Anyone has a question? No. So if that's not the case, so Chris, thank you very much for joining the workshop online, and hopefully see you soon around somewhere.
Yeah, apologies. Yeah? I made the ones in Asia, didn't make the one closer to home. Anyway, enjoy the rest of your day and your visit to the factory. I'm sure that'll be exciting too.
Okay, thank you very much. Yeah. Bye, Chris. So let's thank Chris again. Yeah. Okay, next we have Limbo Jia from Longji to talk about the world record. We only want to know details. Please.
Okay, thank you for Professor Ding's kindly introduction. My name is Limbo Jia from Longji, and today I will talk about the progress of our companies in pushing up the record efficiency of silicon perovskite-tandem solar cells. Next, I will make a specific report from these 3 parts. First, I will talk about why we made tandem solar cells. So, as we know, silicon solar cells is the most popular technique in the PV market, and it is still the leader in the PV market. And the silicon solar cells undergo several important breakthroughs during the past decades. The earliest silicon solar cells featured an LBSF structure, and then PERC, HBC, and TOPCon AJT and technology have been developed to further enhance the device performance. And in recent years, our company has focused on the silicon solar cells and also have made great, impressive progress in silicon solar cells and continuously set the new world records. And recently, a new world record efficiency of 27.3% has been reported by our company. So we can notice that the efficiency of silicon solar cells is getting closer to its theoretical limit efficiency. So it is necessary to develop new technologies to further improve the device performance and reduce the cost of solar cells. As we can see that the narrow bandgap silicon solar cells face a keen challenge of thermalization losses, which can significantly impact the device performance. And the perovskite materials with an ABX3 structure, where A site usually are organic cations, B site are metal ions, and X site are halide ions. And the perovskite materials have so many outstanding properties, including the tunable optical bandgap and high efficiency, and so on. And the theoretical SQ limit efficiency of single junction is around 33%. So it is urgent to develop new technique to further improve the device efficiency and break through the SQ limit. So we can use a wide bandgap perovskite device at the front of silicon solar cells to harvest high energy photons, and the real silicon solar cells can absorb low energy photons to broaden the photo response. And the most studied perovskite silicon tandem solar cells feature the two-terminal structure, in which a 1.86 EV perovskite is utilized as the front cell. So, as the most shining star in the PV market, silicon solar and the perovskite tandem solar cells will hold great potential in the next generation of PV technology. We can notice that in 2017, the efficiency of two-terminal perovskite silicon tandem solar cells are around 33%. And our company has focused on the high-efficiency perovskite silicon tandem solar cells. And right now, the certified efficiency of tandem solar cells has reached 34.6%. So next, I will talk about the strategies we used to push up the efficiency of silicon solar cells. First, as we know, there are two configurations of tandem solar cells, the inverted and the regular structure. And the inverted structures also have so many advantages, including the lower parasitic absorption and gradient refractive index film structure, which leading to the higher device performance. And in contrast, the regular structure usually utilized the spiral-based HTL, which can lead to an additional parasitic absorption and also induce the instability issues of the perovskite surface. So here we choose the inverted structure to fabricate the tandem solar cells. And also, the texture of silicon structure can impact the device efficiency. And the current high-efficiency silicon solar cells feature the fully textured structures to maximize the sunlight absorption. And the tandem solar cells utilize the front side polished silicon substrates, which can facilitate to deposition of uniform and fully coverage perovskite layers. But the inadequate optical management will limit their efficiency. So a key challenge for the fully textured perovskite silicon tandem solar cells is how to deposit the conformal perovskite layers as micro-sized pyramids. Although this approach can enhance the optical management, but it is difficult to achieve the good passivation of perovskite films. So a front-side mildly textured silicon design aims to make a balance between the moderate optical performance and the favorable passivation of perovskite films, which can lead to the enhanced device performance. As we know, improving the top perovskite solar cells efficiency can also improve the efficiency of tandem solar cells. Here we can notice that the bare perovskite layers exhibit lower QFLS values because of different defects of perovskite materials. So our company focused on the additive engineering and the interface engineering, both of the buried interface or top surfaces. Here, First, I will talk about the bulk passivation. As we know, polycrystalline perovskite films contains different types of defects, no matter at the grain boundaries on the surface. Here, we choose bifunctional molecules to passivity defects, which contains a functional group A and another functional group B. Here, for example, we used BDA chloride materials to passivity defects from the SEM and PL measurement, which suggests that this additive can enlarge the grain size and also enhance the lifetime of perovskite films. So, by implementing the bulk additive strategy by using this additive, we achieved an enhanced device performance and reduced VOC loss of 20 millivolt. Apart from the bulk passivation, we have also focused on the top interface passivation. From the PL mapping measurement, we can notice that the bulk perovskite films without any caping layer exhibit the higher PL intensity. But when we direct deposition carbon-60 on the perovskite surface, we can notice that the PL intensity decreased very fast, and also the lifetime is it decreased very fast. So we suppose that there is a high defect density and corresponding non-reactive recombination loss at this side. So in order to address this issue, we introduced an EDI and a lithium fluoride bilayer to passivate the defects between this interface. So we can also notice that after we incorporate this bifunctional layer, the PL mapping intensity and also the lifetime of perovskite films is enhanced. So we think by using these strategies, we can minimize the non-reactive recombination at this interface. Next, in order to prove the interface properties of our materials, we first use top themes measurement to monitor the distribution of these materials. And we have also used other strategies to confirm the distribution of these materials. But the time elimination, I just show the top themes measurement. So from this measurement, we can notice that the EDA molecules did not penetrate into the bulk perovskite, and lithium fluoride and EDI materials are mainly localized at the surface of perovskite films, and they are intertwined with each other. And also the ultra-thin lithium fluoride layer is discontinuously, and the EDI molecules locally contact the perovskite across the lithium fluoride layer. So the EDI materials can form a point contact between perovskite films and carbon-60 to passivate the defects of perovskite films, and also can provide another path to facilitate the charge transfer. Furthermore, we use DFT calculation to investigate the interaction between these materials and the perovskite films. We can notice that the EDAI materials exhibit the higher binding energy, so which suggests that it will form a strong coordination interaction with perovskite films by the chemical passivation. And also, we use KPFM measurement to investigate the interface electrical field distribution. We can see that after we insert this bilayer interface, it exhibits electrical field spikes here. So this interlayer can form a built-in field at this interface, and by this interface dipole, which can facilitate the charge transfer and improve the charge separation at perovskite and the carbon-60 interface. So we used this bifunctional layer to construct perovskite-silicon-tandem solar cells. From the statistic box plot of our device parameters, we can notice that after the lithium fluoride and the EDI bifunctional layer-based device exhibit higher voltage and the enhanced field factors. So finally, we achieved a certified efficiency of 33.9%. And also, we checked the stability of our device by using this bifunctional layer. And both of the storage both of the storage stability and the operational stability are enhanced based on these preservation strategies. And finally, we have also focused on the buried interface optimization. We know that the work function of HTL materials and also the whitening property can help us to form the good crystallinity of perovskite films and also facilitate the charge transfer. So here we designed and synthesized a novel HTL materials to replace the commonly we used materials like 2-PSZ, 4-PSZ exactors. And here, by using our materials, we achieved excellent whitening properties and also improved the energy level alignments between perovskite films and the TCO. So by using these materials, we can finally achieve an enhanced voltage to nearly 2 volts. And finally, we achieved a new world record efficiency of 34.6%. This figure shows the program we did for the perovskite and silicon tandem solar cells. We have done so many works, and right now we achieved a new world record efficiency for silicon and perovskite tandem solar cells. Apart from the small area tandem solar cells, we have also aims to fabricate the large area tandems. And right now, we achieve a new world record efficiency of 30.1% for the commercial M6 wafer size tandem cells. In summary, we focused on the perovskite top perovskite solar cells to optimization the efficiency of tandem solar cells. We focused on the interface preservation and also the bulk preservation. Here, first we introduced a bifunctional layer between carbon-60 and perovskite to preserve the defects between this interface, and the minimized non-radiative recombination, finally leading to 33.9% performance. And then we have also focused on the bulk preservation. We use a bifunctional materials additive to preserve the defects at the green boundaries or fill the added vacancies simultaneously. And finally, the higher crystallinity of perovskite films and a long charge carrier lifetime lead to the reduced VOC loss. And finally, we focused on the buried interface optimization. We introduced new materials we designed, and these materials can improve the energy level alignment, and also it has a good whitening properties. So finally, by using these materials, we achieved a 34.6 new world record efficiency. And although the efficiency of silicon solar cells is high, but the long-term reliability of perovskite-based tandem solar cells also needs to be addressed for commercialization. That's all about my report. Thank you for attention. Thank you so much.
Okay, thank you, Limbo. So every time it's very impressive to see what you have. Anyone wants to ask a question? We have some time. Please, Thomas.
For the HTL, is it also a self-assembled monolayer that you're using or that you developed in-house? Or can you comment a little bit more on the HTL that you used in the 34.6% cell?
You mean the HTL materials we used?
Yeah.
Yeah. We designed a new HTL materials. It also based on the traditional materials. We optimized the side chain of the carbonyl, and also we add functional groups on the carbonyl core to form a defect preservation at the buried interface. And also, we optimize the configuration of these materials. This can form the arrangement of these sums to facilitate the charge transfer. And we also find that our materials can form a good cover ratio of sums, because the good cover ratio can prevent the direct contact between perovskite and the TCO, and this can reduce the contact resistance. Yeah.
Very good, thank you.
Yeah, thank you.
Just to come back to the first talk, what is the highest efficiency you can do with magnesium fluoride instead of lithium fluoride? Yeah, so instead of, if you don't use a lithium fluoride, you use a magnesium fluoride, what is the highest efficiency you could get? I suppose you have tried both. Yeah?
Maybe I right now I don't have idea.
Yeah, you know?
Yeah, maybe we can communicate later.
Okay, all right, thanks. So let's thank Limbo again. Okay, so next we have Perrine Caro. Is correct? No.
Carois.
Huh, sorry?
Carois.
Carois, okay. Perrine Carois from CA. So she's also a coordinator of the project Nexus, which is an important new project dealing with Perovskite-SHJ-Tandem. So, Perrine, the stage is yours.
Thank you for the introduction. Hello, everybody. So we'll take a few steps back in terms of the efficiency after the Langui presentation. So I'm presenting the results of, a small selection of results after the first 2 years of the Nexus project, Horizon Europe funded project. Nexus stands for next generation of sustainable perovskite silicon tandem cells, and it aims at developing high efficiency, sustainable perovskite on silicon tandems that includes solvent-free wide-band perovskite absorbers based on vacuum processes, sustainable bottom cells, so meaning switching from the thick, expensive float zone wafers that are commonly used in the community to the most commonly used industrial Shoklavsky wafers in the PV industry, and also reducing indium and silver content in the cells. We want to deliver industry-compatible bill of material for the module that will be assessed in terms of reliability with the standard indoor testing, but also in a real-life conditions with outdoor monitoring. And we want to anticipate the future of the technology by doing theoretical work to assess if the technology is economically viable, if it can be scaled up, also to assess its environmental impact and if it's socially accepted, and also if it can be compatible with the circular economy. So I'm here on behalf on a big team that comes from 13 organisms all over Europe and also including Turkey, pluridisciplinary team with university labs, research centers, and also industrial partners that can cover all the very different topics of the project that we'll get into now. So as I was saying, for the perovskite offset, we are normally focused on a vacuum processed perovskite, so mainly co-evaporated materials where all the perovskite precursors are sublimed together. The partners develop either methyl ammonium-based perovskite, but also formamidinium cesium-based. And we are also developing more as a risk mitigation approach if in case we don't reach sufficient efficiency with all vacuum process, the hybrid process where the inorganics precursor are first processed in vacuum and then the organic precursors processed in solution, which we still find acceptable in terms of environmental friendliness because the solvent you need for this organic step can be only alcohol-based, so you still avoid the nasty solvents you use for the full, when you fully process the perovskite with the solution. So it's a bit more challenging to get to high efficiencies with the vacuum process, but we have hit almost 20% with the MA-based perovskite. And also in a 165 EV band gap, which is probably close to a world record for this kind of band gap for vacuum processed perovskites. Then we want to make sustainable tandems on sustainable silicon bottom cells. So when you start from a silicon bottom cell that is based on this very thick, expensive float-zone silicon, the first thing you have to do to go sustainable is to replace it with Shokradski silicon that are typically used in the PV industry. Because well, it's mandatory to be economically viable, and also by reducing the thickness, you avoid a lot of automatically avoid a lot of CO2 emissions. So I want to state that from the start of the project, all the tandem devices were made on these CZ wafers that are commonly used for the PV industry, and also the heterojunction technology was processed entirely with industrial processes in the pilot line at CA. So most of the devices, but we're also exploring the TOPCon technology with the Gunam pilot line in Turkey. So the choice of going to CZ wafers is quite challenging for Perovskite-Tandems, because of course you all know that you purchase them as cuts after the sewing process. That leaves a very defective and rough surface. So you have to think how you want to etch this surface and how you want to tune it for perovskites. Of course, as we are doing vacuum process perovskite, you could think, well, just a normal micrometer size texturing could be just fine, as the vacuum process perovskite might just be very conformal on these micrometer parameters, which is what we actually see on the same images. But we still really struggle with the reproducibility of the devices that often have shunts, and the efficiency are now only over 23% for the tandems on this morphology. So we have been developing as well the nanotexturing, so doing less than 1 micrometer parameters. That also brings its own challenges. Well, of course, first thing is to reduce the parameter size, but it is now quite easily achievable with the commercially available surfactants. But it doesn't make sense to make small pyramids if the underlying topology that is left by the soil damage removal etching leaves like patterns that can be a few micrometer deep, unlike when you do texturing on a float zone, mechanically polished, which is completely flat. So we also worked a lot on this SDR process to get a surface as smooth as possible on the CZ wafers before doing the nanotexturing. And the integration to the net device is in progress, but it seems that the first results are promising. Then we want to make modules out of these tandem cells, and of course we want to still stick on commercially available materials. Of course we had to adapt the process to make it compatible with the perovskite, so in particular keep the temperatures low. So for the interconnection we choose electrically conductive adhesive to achieve proper ribbon and adhesion, and we worked out a process that would keep the temperature below 150 degrees. And for lamination, we also purchased a commercially available encapsulant and edge sealant. So we started with a polyolefin elastomer, on which we worked out the process to keep it under 140 degrees. With controlling the first step for the degassing of the encapsulant, and then controlling the pressure and time to ensure the cross-linking of the polyolefin elastomer be sufficiently but below 140 degrees. Then we test these materials on a silicon heterojunction cell, so also including the the edge sealant. And what we observed, some bubbles appearing that we attributed to the organic volatile compounds that come out of the POE when it cross-links. And well, of course, it means that the edge sealant does its job, but we don't want a module with bubbles in it. So we instead changed the POE by a thermoplastic polyolefin. And then we tested again the process with these new materials, and we could demonstrate no humidity ingress with these small stickers. So this is how we came to our first bill of materials for the modules. And after some adjustment on the cells, we were able to encapsulate some first functional devices with limited loss before and after the encapsulation, thanks to the temperature that is kept quite low. And then we want to assess the reliability of these modules. So in real-life conditions, at 3 places in Bolzano, northern Italy, in Valencia, Spain, and also in Ankara in Turkey. And we also have special setups to quantify the lead leaching from precipitations. This is done in Basel and Bolzano to see well, if lead might come from the precipitation that runs on the devices and might contaminate the ground. So we have some first results on monitoring after, so we installed a few samples about 3 months ago. So together with the 2 reference heterojunction cells that were encapsulated with exactly the same bill of materials and processes. So after 3 months, we see that the reference are more or less stable. We see much, so for the tandem cells, we have different kinds of top cell processing and also of wafer morphology. But what we can see, I will not go too much into detail, but that the Perovskite-SHJ-Tandem fluctuates much more. And in particular, we see a strong relation with the performance ratio. So with these cells that perform much worse on the cloudy days and then recovers on the sunny days. And for some cells, it's really like a perfect correlation. And as I was saying at the beginning, we also are doing a lot of theoretical work to assess the sustainability of the technology. So one aspect of it is its environmental impact. So for this, we conducted a cradle-to-cradle environmental LCA, comparing baseline Perovskite-Tandem structure with mainstream silicon and with the kind of nexus technology that reduces some elements that sources the silicon in Norway, for example. And of course, we see that already just thanks to the better efficiency, you can reduce the impact on different categories compared to the mainstream silicon. Of course, going even further with the Nexus optimized structure. And we see 3 main impact categories that are, of course, climate change, impact on fresh water, and metals and material resources, which appear to be actually the most important, the most impacted categories, which leads me to the importance of circularity to assess it. And we have a team in Basel that tries to recover materials from the perovskite, so from hot water extraction to extract the lead iodide, and then from the solid here, it's full of indium and silver. They can recover it with acidic extraction and then can separate them with nanofiltration. We have also assessed the economic viability with the life cycle costing and several criteria to assess the influence. Of course, the lifetime is probably the most impacting criteria, but we have seen that with a 30-year module that can survive 30 years, let's say, and in an optimistic scenario, we can have an LCOE below 2 cents per kilowatt hour. So to conclude, I just want to make a comparison of the current progress of Nexus compared to the state of the art or state of what is most published in the community. So most of the depth level reported deficiencies still are include a spin-coated top cell. They are based on mechanically polished float wafers that may be subsequently textured, but it's not the same as on starting on a ASCII wafer. There's not enough insight on stability yet. There are also very few results with vapor process top cells and not many results yet on tandem modules and no real attempts to reduce solvent raw materials. And at Nexus, we have top cells that function quite well. We work on industrial bottom cells. We are reaching now with these sustainable processes, 23% with the vacuum process top cell and 27% with the hybrid. We have first functioning modules that are now outdoor, and I have not seen it here, but we have successful reduction in indium and silver at subcell level, and we have a proof of principle for the circularity of the technology. And I want to thank the wonderful Nexus team to conclude.
Okay, wonderful. So do we have anyone wants to ask a question? Maybe I have one. Have you encountered any issue with delamination during the lamination process for the perovskite?
No, not really on the perovskite. A little bit with the contacts, metal contacts. We have to over the cell that we had to improve a little bit. But apart from that, no. The cell material themselves, they were okay.
Okay, so all right. Yeah, thank you very much. So let's thank Perrine again and also all the speakers. Thank you. So the good news is we are perfectly in time for the next session. Forgo the coffee break. No, I'm just joking. So before I can leave you out of the session, I would like to ask Cosimo to...
Thank you. So before going to the coffee break, I am pleased to introduce Professor Francesco Priolo, Rector of University of Catania, and Stefano Lorenzi, CEO of Trisan, for a brief speech and welcome.
So first of all, I mean, I should apologize for not being here with you yesterday, but unfortunately I was in Rome, so I arrived today, and it's a great pleasure to actually welcome you in this very old and historical place. We are in this Benedictine monastery that was built in the 1700, and that actually the old structure is even before. There are Roman ruins underground and also a medieval monastery that is around. And this place was touched by a lava flow, the last lava flow that reached the city of Catania in the mid of the 1600, and then it was rebuilt. And today, this is part of UNESCO cultural heritage. And we are very, very lucky to have restructured all of it, and this is now part of our university and belongs to the Department of Humanities. And I think it's very significant that a historical place belonging to the Department of Humanities, that is UNESCO heritage, actually is now hosting such an important conference, such an important workshops that looks at the future, because of course looks at energy and at energy transition and at photovoltaics, at solar cells, and therefore I really welcome what all of you are doing, and I should congratulate with Cosimo Gerardi, Marina Foti, Tony Terrasi, all the organizers for this organization yesterday and today, that I am sure is very fruitful for all of you, and we are very proud as University of Catania to host the workshop in our place. For the strong collaboration that we do have with solar cells industry, and in particular with Trisun, and therefore I'm very, very glad and honored that we have here the CEO of Trisun. I know Stefano Lorenzi, and I know that actually you will visit the factory this afternoon. So let me welcome you again, and thank you for coming, and hope that you are enjoying your stay in Catania.
Thank you, Francesca. Okay, well, first of all, I'm very honored to be here the second day of the International Workshop for Silicon Heterojunction Solar Cells. My gratitude to our rector of the University of Catania and his kind words. I also want to thank all of you for traveling across the world and making this event possible. You researchers, innovators, experts, thank you. And a big thanks to the people who have made this event possible. So I'd like to join the director to thank Marina, Cosimo, and all the people who made this event possible. Please join me in a big round of applause. Thank you. So very short couple of considerations from my side. I believe the photovoltaic sector still holds a lot of potential. And as a former researcher myself many years ago and on different industry, I do appreciate a lot the importance of collaboration at global level. And I think an event like this is a very good platform for having talents, ideas, connecting together and thriving. I think, to this respect, it's also important to remark that Europe has to keep playing a very strong role in innovating and investing in research. And somehow, I reckon we have lost a little bit of that in the last couple of decades in different industries, including photovoltaic. And I think Europe has to speed up the level of investment in new technologies like photovoltaic. In Trisun, we are very proud to be at the forefront of this movement. We are feeling really to be pioneering this movement of reshoring PV industry to Europe, and create and keep having this level of global collaboration on new technologies. Trisun has done a lot of work in the last couple of years to build the first gigafactory here in Catania. And I've joined the team only 1 year ago, and I'm very proud of what a very group of very talented people have made possible. And a couple of months ago, and I just want to remark this, we have crossed a very historic moment of starting production of the first tens of thousands of modules. And this is just a start of a journey which will bring us to full capacity, 3 gigawatt capacity by the end of next year. The 3 gigawatt could sound something normal for the the one of you who come from Asia, but for Europe and for Italy is a tremendous numbers. The 800,000 cells, the 14,000 modules per day are numbers that are kind of scary from sourcing, production, logistics, organization. It's very impressive. And I really like to welcome you this afternoon in Trisan so that you can visit our premises, our 150,000 square meter premises. It's impressive. You will see things in real, not just through PowerPoint, which is also always a nice thing to do. And so I really look forward to hosting you this afternoon in Trisan. Thank you very much for your time and dedication, and safe travels.
Peach, I think that now we can go, no? To go to for the coffee break. Okay, half an hour, so please enjoy.